So indeed, yeah, thank you all for coming. What I'm going to present is some joint work we did with Sander Hilding, Johannes Karenidis. So what we did is kind of to provide an optimization and a gradient descent perspective on some quantum linear system solvers. Well, so actually, why do we even do this? Because these quantum linear system solvers and in general, like fast quantum linear algebra, it is one of the key building blocks of what people call like quantum machine learning. So in more detail, what do we do? Indeed, first we start with exploring this connection of quantum linear system solvers and convex optimization. Then we proceed by proposing an alternative quantum algorithm for inversion, or more specifically, an alternative polynomial that is known to be optimal in some sense. And we proved that this thing can be actually implemented quantumly. And finally, we just consider some lower bounds to see where we stand. So, just as a small reminder about some general facts about quantum linear algebra via block encodings. I think Frédéric already introduced some of these, but let's just go through it quickly. So what are our assumptions? We always start with some n by n matrix A. We can assume that it's Hermitian or symmetric. That has norm bounded by 1. And we have another vector B that is just any random n-dimensional vector. So the key tool we'll be operating with is this block encoding. So what is a block encoding of a matrix? Well, it's simply just a unitary matrix that contains our matrix A as its top left block. So this is there exist some circuits that can implement block encodings for matrices A given in different ways, such as classical descriptions, such as sparse access to A, and so on. So this is kind of doable. And on the other hand, we also consider this state here. We also consider this state here, this cat B, which is just the normalized version of vector B. And immediately you see that if your input matrix is n times n, and if your vector B is of dimension n, the number of qubits on which this unitary here acts is of the order of log n. Similarly, the number of qubits on which this state lives is also around log n. So this is kind of the basic intuition. Why do we get these kind of exponential speedups in quantum machine learning? So just to see the most basic algorithm of fast quantum linear algebra, it's actually just matrix vector multiplication. So what we do, we don't do anything smart. We just multiply our blocking. We just apply our block encoding circuit to the normalized vector, and we see that we get, as a result, we get our desired matrix vector product. Yes, and if we measure this state, we will actually get a state corresponding. If we measure the first qubit of this state, we'll get a state corresponding to the matrix vector product that has amplitude proportional actually to the norm of this product. So yeah, so kind of we can do some post-selection and determine whether we succeeded in doing this matrix vector product. Okay, so this is all well and nice, but it's not very surprising. What's more interesting is whether we could do some more interesting manipulations with this. So, for example, could we implement the inverse of A, a block encoding of the inverse of A? What about some polynomials, or even some like f of A's for some nice functions f? Well, for a start, maybe you can say, this is quantum mechanics. It's purely linear, it's purely unitary, so there is no way that we can do this. And then you also have a more algebraic argument so even if your input matrix A is bounded by 1, the norm of the inverse can be large. So we will have problems constructing block encodings of this. And finally, speaking of more general functions, we would somehow need to implement this function and evaluate it on A, which can have arbitrary eigenvalues between -1 and 1. But we are not allowed to do any explicit eigenvalue manipulation. So we are not, maybe classically we would be able to do some kind of eigenvalue decomposition, do some transformations with the explicit descriptions of the eigenvalues, but here is not possible. However, here you see kind of a toy example that actually it is possible to induce a non-linear transformation on a single entry of a 2x2 matrix purely by doing unitary transformations. So what we do is that we define kind of this reflection matrix R that depends on our data. So it kind of, the important part is that it encodes our interesting value X. And then we somehow intersperse it with some of these rotations, with these rotation matrices here. And it turns out it's very easy to see that no matter which angles phi here you choose, you always get a polynomial in the resulting 2x2 matrix. So, okay, we are getting there, but it is still unclear which are the polynomials that we can achieve here. And for a long time, this method of coming up with angles, as the authors say, was more art than science. However, finally, in 2016, Low, Euler, and Chuang, they proved that we can get epsilon close to any polynomial p of degree t, provided that some two technical conditions hold. So what are these conditions? First of all, okay, we have a disparity constraint on p, that it has to be odd if the degree is odd and even if the degree is even, and more importantly, that it has to be bounded by 1 for all x's in this interval -1, 1. So I'll just mention it immediately here, is that this first constraint here is easy to overcome. Somehow, you know that all functions can be written as a sum of an even and odd function, so this is kind of easy to overcome at almost no cost. However, this second constraint, this bound constraint, is much more fundamental. But in any case, so first, we would like to extend this, this nonlinear transformation to matrices. Indeed, it turns out that this can be done, and this was done by Guillen, Su, Low, and Wiebe in 2018. And it turns out that what can be achieved is applying the same polynomial p, like the same class of polynomials p, can be applied to the eigenvalues of A. And they call this algorithm the singular value transformation algorithm. Why singular values? Well, there exists a more general version that, that accepts some broader class of inputs that actually applies your polynomial to the singular values. But here we are interested only in the eigenvalue case. So how does their circuit look like? Well, basically, it has a similar structure to what we had before. So before, we had our variable matrix interspersed with some rotations. And here, we have something very similar. So we have our block encoding of our initial matrix A interspersed with something. Well, what is this something? This something is basically a controlled rotation. So a controlled rotation by the same angle phi. And what's it controlled on? It's controlled on this state kind of being in the interesting block of A. So kind of this pi, it verifies whether we are in this upper left block of our block encoding. So yeah, this is very nice. We have a very general result, and it turned out that indeed it's some kind of a unification of many existing quantum algorithms. And these angles here, they can be found. However, somehow the algorithm for finding them, at least as initially described, it was based on like some series of lemmas upon lemmas, and what's more, it was not the most numerically stable algorithm that you can get. Somehow it operated in the monomial basis, and we all know that the monomial basis is not the best way to represent your polynomials if you are always bounded on the interval -1, 1. However, speaking of basis and stability, it turns out that there exists an alternative basis, actually, basis of these classical orthogonal polynomials called Chebyshev polynomials, that are in some way the best basis for operating on this interval -1, 1. In particular, what do I mean by best? Well, imagine that you have your some function defined on the interval -1, 1. You find its expansion, you find its Chebyshev expansion, its series, and you truncate this series. Well, this truncation is actually going to be the quality of the approximation is going to be very close to the quality of the best minimax approximation of the same degree on this interval. What's more is that the angle sequence phi for the singular value transformation framework is very simple. We have a closed form for these angles. Just the first angle is kind of 1 minus the degree times pi half, and the rest are just pi half. So we know how to implement these Chebyshev polynomials via the singular value transformation framework. And finally, what's also important is that there exists an efficient algorithm for converting a polynomial in the monomial basis to the Chebyshev basis. The complexity of this algorithm is almost linear in the degree of the polynomial, and it's based on the fast Fourier transform. What I would also like you to pay a bit attention to is just the fact that these polynomials are nicely bounded between -1 and 1. This will come in handy later when we talk about some proofs. So, as I said, the angle sequence for these Chebyshev polynomials is known. So it turns out that the circuit for implementing a block encoding of a Chebyshev polynomial applied to a matrix A is also very simple. In particular, it has this form. So it starts with the block encoding. Okay, so we just restrict ourselves to the case of odd polynomials for brevity. So how does this block encoding look like? Well, it's just a single application of the block encoding of A, followed by the Th power of some simple to construct matrix. So yeah, these circuits for implementing these block encodings are all prefixes of each other, which means that we can evaluate all odd Chebyshev polynomials just by selectively applying parts of this circuit here. So what do? We basically do this famous square and multiply trick where we just choose the right powers of W that we are interested in. Okay, so we can implement these polynomials. It's all very nice. And just as a bit more of an argumentation, maybe to convince you, is that in the 1D case, this W matrix is just a rotation, like a 2D rotation matrix by the angle 2 theta. So you can even verify yourself that this circuit here indeed implements the Chebyshev polynomials. So now we can describe what's the mainstream, what's the standard inversion polynomial that's usually used. So we consider this polynomial here. Let's just unpack it for a bit. What is it in fact? Well, it's basically the inverse. However, in order to make it a polynomial, we subtract some small function, some function that is equal to 1 at 0 and almost 0 otherwise. So kind of this construction gives us a real polynomial of degree 2t minus 1. And since obviously our inverse function is unbounded at the origin, we have to restrict ourselves to approximating the inverse only on this specific interval. So the unit interval minus the small interval from -1 over kappa to kappa, where the inverse is too large. So indeed, it turns out that this PT that I described, it epsilon approximates our inverse on this domain for some degree that scales roughly as the square root of the condition number kappa. So an obvious consequence of this is that we can implement a block encoding of the inverse provided that all eigenvalues of A are contained within this domain here. So this is nice. This is a nice first step. However, we can go further. So what we do is that we develop our polynomial PT in the Chebyshev basis. This allows us to conclude easily that the polynomial is bounded by the degree and its odd on this interval -1, 1. However, what can be noticed and what can be proved is that we can truncate this expansion after only O of kappa terms. And this was proven by Charles Kothari and Soma, that actually an O of kappa degree polynomial obtained in this way is sufficient to epsilon approximate the inverse. So here, okay, here we see this polynomial, or rather, we see the inverse. This is this red line here. And we see the approximating polynomials of varying degrees. And the only thing that we need is for these polynomials to approximate the inverse well outside of this blue strip here. However, as kind of always with these quantum linear algebra algorithms, there is some fine print. There are some problems. First of all, as I said, in order to apply singular value transformation, in order to evaluate our polynomial at a matrix, we need to bound it. So we need to bound it by some m, and then we evaluate our polynomial that is rescaled by this bound. However, so how can we do this? Well, again, by noticing that the Chebyshev polynomials are bounded by 1, we conclude that the bound on our polynomial PT on the interval -1, 1 is actually the one norm of the Chebyshev coefficients. And this is also an object that will be interesting afterwards. So indeed, yeah, this allows us to conclude that the norm, or yeah, this normalizing factor m is almost linear in kappa. Putting this together, okay, this allows us to implement a block encoding of A inverse that is subnormalized by kappa. We need to amplify this. Via standard techniques, we can amplify it. Via standard techniques, the total cost of the algorithm is roughly kappa squared. However, there are some smarter and more advanced techniques that allow us to have a complete matrix inversion algorithm in O of kappa. So this is all kind of well known. Now we switch gears a bit and we change to iterative methods. So how do classical people solve linear systems if the matrix A is too large? So obviously, yes, you can do Gaussian elimination. The cost of this is like around n cubed or so on. But there exists another class of algorithms, like these iterative algorithms, whose cost is proportional to the condition number of A and some matrix vector multiplication. So in particular, what we do, we consider this function here, this quadratic function here, and we just want to minimize it via gradient descent. It's easy to see that the minimizer of this function is actually the solution to our linear system. So what we do is, indeed, we have a very simple iterative method. We start from some vector, and we proceed to do some very simple linear updates. In particular, if we simplify like the constants to 1, it turns out that the entire algorithm actually can be viewed as implementing, as evaluating a polynomial at A and applying it to B. So now we somehow start seeing connections to the quantum algorithms. In particular, yeah, so standard theory tells us that for solving such a system, O of kappa squared iterations suffice, which is actually the same as the degree of our polynomial PT that we defined before. So this is already surprising. And then the obvious question is whether we can do something better with some higher order methods. Because, okay, gradient descent is a first order method. We know that it's not very interesting, but maybe we can do better. So classical theory, again, it tells us that we cannot do better than second-order methods anyway, with the guarantees that we have, that our function is just strongly convex. So what is the best second-order method? Well, it turns out that this is known classically, and this best second-order iterative method for solving the linear system is the Chebyshev iteration. So how do we derive it? Well, we just ask for what is the best polynomial that minimizes this difference on our domain of interest. We can consider some polynomials of this specific form. In particular, it's kind of the inverse, just like what we had before, minus a function that is equal to 1 at 0 and small elsewhere. By these extremal properties of the Chebyshev polynomials, we have an exact expression for the optimal polynomial. And indeed, it turns out that the resulting polynomial epsilon approximates the inverse on our domain of interest with degree O of kappa. And so we don't need any truncation ideas. We don't lose the iterative nature of this algorithm. In particular, the iterative nature of this algorithm can be derived from this recurrence satisfied by the Chebyshev polynomials. So indeed, you can get to a real iterative method that updates your vectors via simple matrix vector products. So this is one of the two slides with the technical results. So again, what do we need to do in order to make this work? Well, we need to bound our polynomial. Okay, so in general, it approximates the inverse, so it should be kind of fine. However, on the interval from -1 over kappa to kappa, we have a problem. We don't really know what's happening. So we have to do the same thing again. We have to bound the one norm of these Chebyshev coefficients here. The problem now is that there is no closed or even no nice form of these coefficients. So what we do is indeed, we prove that this all works out, that we can approximate the inverse on this domain with degree kappa with this subnormalization here. So this subnormalization here is linear indeed, just like what we had in the case of the standard polynomial from Charles-Kottari and Soma. However, we have this explicit constant that we'll see that it's better in practice. But we'll get there. So just one word on the proof techniques. Maybe I found this nice, so maybe it's going to be useful to somebody at some point. So what we use is that we use this discrete orthogonality property of Chebyshev polynomials. Basically, yes, this is an analog of the classical, of the more well-known continuous orthogonality property. So what we do to compute these coefficients, well, it turns out that this is just a simple matrix vector multiplication, where this matrix here, you can think of it as the Vandermonde matrix, but for the Chebyshev polynomials. So in this case, it turns out that this thing is extremely well conditioned. It has a very nice norm. So the thing that we have to concern ourselves with is actually our polynomial Qt evaluated at some specific points. What are these points? Well, they are the roots of the Chebyshev polynomials of degree 2t. So this can all be done, and actually we can prove this bound on our Qt. So finally, here are some maybe more practical things. So here we see the comparison of the errors we get with the older, more standard Charles-Kottari-Soma polynomial and our polynomial here. So for the same degree, we get a much better error. So what does it mean for practical purposes? Well, either our circuit is going to be simpler, we are going to use less qubits, less gates, and so on, or we can achieve higher precision approximations to the inverse for the same cost. Finally, okay, I'm going to maybe skip over this. And finally, we get to some lower bounds. So yeah, now we have this nice O of kappa upper bound. How do we stand? What's the situation from the lower bound perspective? Well, it's been known already for a long time that the query complexity, which Simon introduced so nicely in the last talk, that the query complexity is omega of kappa, provided that we can sample from the solution of the linear system. Furthermore, this is true even for positive semi-definite systems, which is kind of surprising because classically we know that these iterative methods give us off-root kappa algorithms. So somehow it's a bit strange that we get an omega of kappa here, but okay. And finally, maybe what's also interesting is what's the bound in terms of n. So classically, we know that in order to solve our matrix, our linear system, we need to query all the entries of our matrix. So yeah, classically, we do have n squared. So do we have n squared quantumly as well? Well, yes, if we want a classical output. The big question is what happens if we want a quantum output. And this is kind of still open. So yeah, maybe I'll just go back here. This technique for decomposing in the Chebyshev, for decomposing our interesting function in the Chebyshev basis, it is a bit more general. Like we can apply it in a bit more cases than just for the inversion. How exactly? Well, we already know how to compute these block encodings of Chebyshev polynomials evaluated at the matrix A. So the only thing that we need is to find their linear combination. And actually, we do have this linear combination of unitary framework that can achieve this. And in particular, like a key ingredient to implementing it efficiently is implementing the following unitary here. And this unitary here can be implemented efficiently because of the particular structure I mentioned about the prefix structure of the block encodings. So the end result that we get from here for any arbitrary function with this Chebyshev decomposition is the result that we want, that is subnormalized by the one norm of the Chebyshev coefficient. So they pop up again. And what we can prove again is that this technique can be used for evaluating powers, normalized exponential logarithms, and even discontinuous functions such as sine. However, we somehow numerically, it seems that for Hamiltonian simulation, or rather implementing this function here, it turns out that the one norm of these coefficients is too large, and our method is not as efficient as SVT. So this is also a question. Why do we have this gap in the case of Hamiltonian simulation, but not for some much harder functions to approximate? So indeed, I'm going to recall all these open questions that we had. So first of all, can we actually get a real quantum iterative method? So for now, these methods are kind of iterative, but on the other hand, they take the entire iterative method, they squish it into a single polynomial and evaluate this polynomial. So this is somehow unsatisfying a bit. So can we have like true quantum iterative methods that are at least as efficient as their classical counterparts? Second question, whether in terms of lower bounds, can we get a real omega of n squared query bound for inversion if we allow quantum output? What's the situation in the case of related problems where we are only interested in the sampling from this inverse vector, whether for A, P, S, D or not, doesn't really matter. And finally, maybe a more specific question is why do we have this separation between singular value transformation and this Chebyshev decomposition technique in the case of Hamiltonian simulation? So yeah, that would be it.